Stanford University.
Let's review a little bit, and then I want to move on to generalizations of what we've talked about so far. I think we worked out the equations of an expanding universe. There were Newton's equations. Let's talk about something else first. Does Newton's equations really get it right? Yeah, Newton's equations does get it right for the most part, and let me explain why. Einstein's equations have to do with curved space-time. Now, the universe that we're ultimately going to study has curved space-time, all right, and in fact, some versions of it even have curved space. That simply means that space itself, forget space-time, just space itself, if you measure triangles on it, if you do various kinds of geometric exercises on it, you'll discover perhaps that space is curved. At the moment, it looks pretty flat, but it's possible that it will turn out on the average to be curved. And if it is curved, well, maybe it looks like a three-dimensional version, let's say, of a sphere. Well, we're going to study later, not tonight, maybe partly tonight, it's a portion of a sphere. That's a portion of a sphere. We're over here. We look out. We can only see so much. We can't even really see that the sphere is curved. Okay? But at a large enough distance, we may be able to see that the sphere is curved. On the other hand, supposing we just decide to look at very neighboring galaxies. Now, very neighboring galaxies can mean 1 billion light years from us now. Very, very neighboring galaxies, much smaller than what we think the radius of curvature of this universe is. Well, then it looks flat. And if it looks flat, it should mean that at least for that portion, if we're not interested in the whole thing, but we're just interested in the local nearby behavior, we should not have to worry about the fact that it's curved. If that's correct, then it means that the way these galaxies move relative to each other and how they move apart from each other, at least in the small here, can be studied using Newton's equations. That's what we've been doing. We've been looking at the universe in the small and studying how a small little fraction of it is expanding or not expanding, whatever it's doing. And it's perfectly legitimate and, in fact, entirely consistent with Einstein, with relativity, except for one thing. Except for one thing. We would run into trouble if the galaxies, or whatever is present, galaxies, particles, whatever is present, if they were really moving past each other with a significant fraction of the speed of light. One of the assumptions is that the neighboring things are moving relatively slowly with respect to each other. Something very, very far away may be moving with a large velocity relative to you, but as long as the things nearby are moving with non-relativistic velocities, you can study, relative to you, you can take a small patch of it. Now, small could mean 10 billion light years, okay? But you can take a small patch of it and study it without using any relativity, really. If we discover that there are particles moving with close to the speed of light past each other, then of course we will have to modify the equations. But there are particles moving fast by comparison with the speed of light past us. What are they?
Neutrinos.
Well, neutrinos for one, but photons. Now, I don't mean photons from the sun. I mean photons that would be there even if there was no sun. The universe is filled in the same way that it's filled with galaxies. It's also filled with radiation, homogeneous radiation. And that homogeneous radiation does move with the speed of light. That means that we have to modify our equations somehow to account for this very, very fastly moving, rapidly moving material, photons. We're going to do that tonight, but I want to just review what we did last time quickly. We first of all said, suppose that space is homogeneous and filled with galaxies, and I'm not going to try to draw all the galaxies. They form a gas, if you like, that kind of fill the blackboard with a certain number of particles per cubic meter. In other words, a density that we called Rho. And that was the content of the universe in kilograms per cubic meter, if you like. You could use some other units, but whatever units you like. Physical units, kilograms per cubic meter. And we called it Rho. We laid down a grid on this universe. And in laying down the grid, there was clear ambiguity. Imagine that we laid down the grid at some specific time, like today. We laid down the grid, and you could ask, what is the spacing between, the grid was a coordinate system, let's call the coordinates x, and the distance between x equals something and x equals something plus 1. In other words, one grid separation here, one lattice separation, there's a certain distance associated with it. How big is that distance? Well, we called it A, but how big is A? That depends on the grid that we laid down. If we laid down a very coarse grid, it would be one thing. If we laid down a fine grid, it would be another thing. And so it had better be that our equations, at least at the moment, do not prefer any specific value of A. We could lay down a different grid. The different grid could be twice as dense. So here's the black forms one grid, and the black and green together form another grid. If we looked at the more dense grid, we would also invent an A. Let's call it A prime. A prime is the distance between neighboring points on the dense grid. That would be 1/2 A. So if you ask me, what is the value of A? I'm going to say, I can't tell you until I know precisely what grid is laid down. And so A itself doesn't have a physical meaning, at least at this stage. Later on, we'll discuss more what A means. But at the moment, on a flat blackboard, it doesn't mean anything by itself until you specify exactly what the size of the grid is. Okay, so A is just a sort of bookkeeping device. On the other hand, ratios of A may mean something. Let me give you an example. Supposing I told you, now A is a function of time. Universe is expanding. The distance between neighboring galaxies, the galaxies are embedded in the grid. They move with the grid. The actual physical distance between galaxies is growing. Okay. Supposing I told you that over a period of time, A doubled. That has meaning. That means the distance between every galaxy, every pair of galaxies doubles. So ratios of A, particularly ratios of A at different times, are recording a history of how the universe is expanding or contracting. And that's why our equations tend to only involve ratios of things with A. Let me give you an example. Let's take A dot, the time derivative of A. Well, that will depend on whether I use the black grid or the black-green grid. Every A associated with the black grid is twice as big as every A associated with the black-green grid. And if every A is twice as big, A dot, the time derivative, will also be twice as big. On the other hand, if I take A dot divided by A, and let's compare it with A prime dot divided by A prime, they will be the same. They will be the same because the ambiguity in the scale of the grid will cancel out. A prime will be a half A dot prime will be a half A dot, you know what I mean? And the factor of 2 will just cancel out. So things involving ratios of A, those are invariant, physically meaningful things. And if you remember, A dot over A is just the Hubble constant at a given time. So it really does mean something. But A itself, an ambiguity in how big it is, but it's a once and for all ambiguity. Once you fix it, then you stick with it. Okay, another thing which is ambiguous was we introduced a constant, nu. Remember what nu was? Nu was the mass contained within a single cubic cell of the grid. In other words, a grid element here, 1 by 1 by 1 by 1. Well, one what? One grid unit. The amount of mass within that cube, which we called nu, is ambiguous because we haven't determined exactly what the grid is. Nevertheless, once the grid is fixed, nevertheless, the amount of mass within a single cube is called nu. But it also changes when you change the grid. Now let's go to the equations that we derived last time. The equations we derived last time, I'll just remind you how we derived them. We took the universe filled with galaxies. We called them particles uniformly, and we placed ourselves right at the center, arbitrarily, but still consistently. We placed ourselves at the center, looked at another galaxy which was at a specific location on the grid, some x on the grid, and we studied Newton's equations for the motion of that galaxy, which you would think would be horrendously complicated because they're interacting with loads and loads of galaxies. But we used the famous theorem of Newton. Well, first of all, we imagined smoothing things out so that we could think of the distribution of these galaxies as smooth and uniform. We took a sphere, centered at us, excuse me, and we used Newton's theorem that told us that relative to us, in the coordinate system where we are at rest, the force on that galaxy only depends on the mass within that sphere, as if all of the mass were concentrated at the center. So we just said, let's concentrate all the mass within that sphere at the center, and then study how, under such circumstances, the galaxy at x would move if it were under the influence of just that mass. You don't have to worry about the masses on the outside. You only have to worry about the masses on the inside, and we worked it out. And the simple way that we worked it out, the simplest way we worked it out, was just to say, if there was a particle over here moving under the influence of a fictitious mass at the center, then the energy of that particle would be conserved. The energy consisted of two terms. Well, I think let me come back to the derivation again. I just want to review the derivation very quickly, but I'll come back to it in a moment. Let me remind you what the equation was. The equation that was derived was that A dot over A squared, that came from the kinetic energy, was equal to the density of matter, rho, measured in physical units, in other words, measured in kilograms per cubic meter, not this new object over here, but rho. And there was a little more. There was an 8, a pi, and a g Newton. That was the equation that we derived by just looking at the conservation of energy. Rho, oh, sorry, you didn't catch me, over 3. That 3 ultimately came from the volume of a sphere, 4/3 pi r cubed. Okay, that's where the 3, that's where the 8 is 2 times 4. Pi is pi, and 3 is 3. This is related to the volume of some sphere. Okay, that was the equation that we worked out. That was in the case of zero energy. That was in the case where the potential energy of this point and the kinetic energy of it exactly canceled. It could also be understood as the situation where every galaxy is exactly at the escape velocity, just on the knife edge between being able to escape and not escape. That's what that formula was. We added one more thing to it, and the one more thing is we said that rho, which is the amount of mass, it's the amount of mass per unit volume, is related to nu. Is it the same as nu? No, because nu is the amount of mass per grid box. But the grid box, you don't know what its volume is. This is the mass within one cube. If you want the density, then the density is related to nu by dividing nu by the volume of one of these boxes. This is density per cubic meter. This is per cubic box. You divide that by the volume of a box, which is a cubed, and that's one more fact that we put in, that rho is nu divided by a cubed. Now, is rho constant with time? No, because a changes, but is nu constant with time? If nu just represents ordinary particles sitting in the universe which are never destroyed, never created, particles of protons, let's forget whether the proton decays for the moment. Protons are forever, and galaxies are forever for a moment. Not forever. We won't believe that forever, but we will believe for the moment that galaxies are forever. Did you get that? Yeah, okay. If galaxies were forever or protons were forever, then nu would be constant. The number of protons within a box is the same at all times. All that happens is the box grows. So the protons thin out, but the number of them in a box stays fixed, and so nu stays constant. What is it? What is its numerical value? I can't tell you what the numerical value is because that has to do with the exact grid that I use. If I change grids, I change nu. Okay, so but in any case, once I've established all of the conventions, I can replace rho by nu divided by a cubed. Nu is a constant. It doesn't change with time. 8 is a constant, pi is a constant, 3 is a constant, g is a constant. All of this stuff here is just a numerical constant. In fact, by judiciously changing your definition of the grid, since changing the grid changes the magnitude of nu, I can, if I like, choose 8 pi g nu over 3 to just be 1. It doesn't make any difference. The point here is that the numerical constant that appears here really doesn't make any big difference to the way the universe evolves. And the way you can see that is by changing definitions of the grid, you can change the constant. So we could, if we like, just set 8 pi g nu over 3 equal to 1, and then we would have the very nice differential equation, a dot over a squared is equal to 1 over a cubed. Now, would you like to see how to solve that? We solved it last time, but we solved it by guessing. How many people want to see me solve it in real time? I know when you want to see me solve it in real time because you're hoping I'll make a mistake. Yeah, you were going to ask a question. Okay. Well, it's too bad. I'm going to solve it whether you want me to or not. Here's the way you solve it. Here's the way you solve all these equations. You first of all take the square root of both sides. On the left side, that's easy. It's just a dot over a. On the right-hand side, it's a little bit of a nuisance. It's 1 over a times square root of a. Do you see where that came from? A cubed is a squared times a. The square root of it is a. times the square root of a. Okay. Let's multiply both equations, both sides by a to get rid of it in the denominator. And that just tells us that a dot is 1 divided by the square root of a. That's where we would like to begin. Okay, now, we're going to write this. dA by dt, which is what it is equal to 1 over square root of a. But now we're going to do something tricky. The very tricky thing we're going to do is, instead of thinking of a as a function of time, we're going to think of time as a function of a. We're going to take a to be the independent variable. And to do that, here's dA dt. That looks like a is a function of time and we're differentiating it. But if I turn it upside down, it's d, meaning taking 1 over it, it's dt dA. And now it looks like it's the derivative of time with respect to a. And that's equal to the square root of a. So how do we solve it? We look for a function of a whose derivative is the square root of a. What function has as its derivative the square root of a? A to the 3 halves, right? Well, 2/3 a to the 3 halves. So we find out that t is equal to 2/3. The 2/3 is absorbed into other constants that we've been ignoring, times a to the 3 halves. All right, we can solve that now. What we really wanted was a as a function of time, but that's easy. If we just neglect the 2/3, I just don't feel like writing it. If we get the 2/3, this tells us that a is equal to t to the 2/3. A is equal to t to the 2/3, which is a function a t, which looks like that. And it gets flatter and flatter and flatter. The flattening of it is deceleration. The universe is decelerating, but it never comes to rest. We could see that it never comes to rest because when we look at this equation, there is no point at which a dot over a becomes 0. How do I know it doesn't become 0? Because the right-hand side is never 0. It gets smaller and smaller as a gets bigger and bigger, but it never goes to 0. And that's why the universe decelerates. Another way to see that it decelerates, it's just a particle moving away from a fixed force center. It will decelerate because of the attraction by the force center. And that was lesson number 1. All right? I redid it because, well, I always think it's worthwhile redoing the most important derivations.
It's okay if we throw away the negative square root?
Yes, it's okay to throw away the negative square root. What's the logic? The logic from the equation, you cannot tell whether the universe is expanding or contracting. Both are possible from the equation. If you start, it's exactly the same deal as saying you have a planet over here. Yeah, coffee is a good planet. Well, and the almond here is a rock. And you see the rock is right over here. The equations of Newton will not tell you whether the rock is moving away or whether it's moving toward. There's one thing you can be sure of. Let's ignore for the moment moving in orbit. Let's assume we know that the rock is moving radially. There's one thing we know for sure, that it's not standing still. It may be momentarily at rest. It might have come up and stopped, but it's not going to stand still. It's accelerating. It's accelerating back toward the planet. Okay? So it could be going out and decelerating, or it could be going in. You can't tell from the equation. The same way, you can't tell from the equation whether it's expanding or contracting, and that has to do with the 2 possible solutions, whether the ADT is positive or negative. If it's contracting, it's negative. If it's expanding, it's positive. Okay.
Excuse me. In sort of all of this, all these objects are kind of moving radially with respect to each other. So,
Yeah.
but of course, I think of all these objects out there. They're all, kind kind of spinning around each other.
Well, okay, so that's right, that's right. But still, on the average, they tend to move as if they were embedded in this grid. Given that they are embedded in the grid, the only option they have is to move radially relative to each other. Now, you're perfectly right. There are motions on top of that average motion. The motions on top of the average motion don't, of course, satisfy this. They're called by astronomers peculiar motion, meaning, I don't know, are they peculiar? Well, I don't know. The sun moves around, sorry, the Earth moves around the sun, and the Earth is not participating in this expansion relative to the sun, but you know, if you go a few galaxies over, the whole thing is. So the real motion of real galaxies is a combination of this average flow. Think of it as a flow, a river going downstream. How fast is any given molecule moving? Well, I don't know how fast any given molecule is moving, but I do know on the average that clumps of molecules sufficiently averaged are moving with whatever the velocity of the river is. On top of that, there's the peculiar motion of the molecules relative to each other. So that's the way to think about it, a flow, and on top of the flow, fluctuation. And we're ignoring the fluctuation at the moment. Okay. There's two directions I want to expand it. No, well, not expand. There's two directions I want to generalize in today. The first, well, probably the second. The second will have to do with what happens if you replace massive particles, galaxies or protons and so forth, by photons, by radiation. How does this whole story look different? If there was a universe, a fictitious universe, which had nothing in it but photons, how different would this be? Now, why am I doing that? What a silly thing to do. Why take a fictitious universe which is only made of photons? Well, what we're going to find is that early on in the history of the universe, the most important thing in the universe was photons. Today, and when I say most important, I mean the largest concentrations of energy. Early on, the most concentrated, the biggest form of energy in the universe was radiation. Today, the most dominant form of energy in the universe is just the masses of particles, E equals mc squared kind of energy. That's what this theory is about. It's about the behavior of massive particles, non-relativistic, slowly moving particles. Yeah.
I thought today it was dark energy.
That's also presumably made of particles that are pretty much standing still. Mm-hmm. Oh. 30 years ago, we would have said that. Right, we're still 30 years back, or 25 years back, or something like that. You're right. Good. Yes. But dark matter, by contrast, is part of this story. So, yes, thank you. That was helpful. Yeah. Well, what I'm telling you now is an old story, but it's a story whose basics are important to us. Okay, two directions I want to go. The first has to do with what happens if the universe is made out of other kinds of stuff other than just particles more or less relative to each other, radiation in particular. And the other is to move beyond the assumption that the energy is zero. There was no reason for that. It was arbitrary. We said arbitrarily, let's assume that every galaxy is moving away with exactly the escape velocity. Let's back off that now. And how do we back off it? We go back to the energy equations and say the energy of that particle moving in the fictitious field, not the fictitious field, but the field of the fictitious concentrated mass at the center. This is not a real galaxy now. This is the combined mass of everything within the green sphere. Particle out here, moving outward, and let's apply the conservation of energy to it. Let's go back through the derivation, apply the conservation of energy, and then see how the equations change when we go away from the limit of zero energy. Okay, so what is the energy of this particle? This whole glob here has mass m. We'll come back to what m is in a moment. But it has mass m. It's not the mass of the sun, and it's not the mass of any specific galaxy. It's the mass of everything in the sphere. Okay, and the energy of this fellow over here is 1/2 m. M is the mass of this fellow, not the big mass in here, the mass of this galaxy, times its velocity squared. That's one term. And then the other term is minus mg over the distance between them. Let's call the distance d, as we did last time. Oops, I missed something, didn't I? Another factor of little m, right? Right. Product of the masses, Newton's constant, distance between them. That's the energy of this particle moving out. And what do we know about it? We know that it doesn't change with time. It doesn't change with time because our model, that's a useful model, is just the motion of a particle in a fixed background of mass. The energy is constant, and so let's set the energy to be equal to some constant. Now, what does constant mean? Does it mean a numerical constant that's independent of everything else? No, it doesn't. It could depend on which particle we're talking about. Could. In fact, if the universe is homogeneous and isotropic, the only real thing it could depend on is the distance away. So I'll simplify the discussion for now by taking this particle to be at x equals 1. In other words, we're going to take a specific particle, a very definite one, at x equals 1 and focus on it. It has some specific energy, and that energy will never change. So let's just call it E. And it's a constant. What value of the constant? I don't know. I can't tell you offhand. No more than I can tell you if I know that there's a nut over here and there's a planet over here, there's no way I can tell you a priori what the energy of that particle is. I don't know how fast it's moving. Right? So we have to study all possible cases. Right? So we just put the energy and call it E and take it to be a constant, a numerical constant. Let's write out now everything. Let's divide this. Let's first of all divide it by m, little m. Let's divide by little m, divide by little m, and then over here we get E over m. Now, E is a constant, m is a constant, E over m is a constant, so I really haven't made it any more complicated by dividing by m. I'll leave it here as E over m, but the right-hand side is just a numerical constant. Let's even do a little more. Let's multiply by 2. It's still just a constant, and since I didn't tell you in the beginning what E was, all I know is that this is a constant. So let's leave it that way. Now, what about the velocity? If this is the galaxy at x equals 1, then its velocity, well, its distance, the distance is a times x. The velocity is a dot times x. And so now we can just plug that in here. And x is 1. I've chosen x to be 1, so it's very simple. The distance of the galaxy is just a scale factor a. It's called a scale factor. And its velocity is just a dot. So let's plug it in here. This just says a dot squared minus 2mg over d, and d is a, is equal to some constant. Now I'm just going to call it c, constant on the right-hand side. This has many of the elements of this equation here, but this equation, this nice equation, we divided by a twice to get a dot over a squared. Why did I do that? Because I knew in the back of my head that A itself is not a meaningful thing. It's only ratios of A's. So in the back of my head, I knew that what I really want to get is an equation for ratios of A's, or A dot divided by A. So I divided this equation by A squared. A cubed. Notice something's happened on the right-hand side here. It's no longer a constant. C is still a constant, but A squared now has something new in it. And finally, we used that the mass divided by the volume cubed. Now, this is a sphere. This is a sphere of radius A. X is equal to 1. A sphere of radius A, and the volume of a sphere of radius A is 4/3 pi A cubed. So I have A cubed down here. That's not quite the volume of the sphere. Let's fix it so that it is the volume of the sphere. Let's multiply. Well, I don't want to botch up this equation too much. Let's rewrite it. A dot over A squared minus twice mg over A cubed is equal to a constant over A squared. But now let's multiply and divide by 4/3 pi. So this is 4 pi over 3. And we have to multiply out here by 4/3 pi. That becomes 8/3 pi. That's where our 8/3 pi came from. Okay, 4/3 pi A cubed over 3, that is the volume of the sphere. And what is the mass divided by the volume? The density. So by fiddling around, I got the Friedman equation, but with a right-hand side now, a right-hand side that knows about the total energy. If C is positive, it meant the total energy was positive. It meant the kinetic energy outweighed the potential. Sounds like, and it does, means that the galaxies are going to continue to recede forever. You've beaten the escape velocity. If C is negative, then the energy is negative, more potential energy, more negative potential energy than kinetic energy. And that's the situation where you expect everything to go out a ways and then come back and crash. So we now have a new equation, the Friedman equation for non-zero energy. The energy can be positive or negative. Positive or negative, both are allowed, total energy. And let's examine it a little bit and see if we can see a little bit what it says. It's not too hard to solve for any given case, but let's not solve it. Oh, one other step. One other step. Let's write it over here. A dot over A squared. And let's transpose this factor to the other side. Equals 8/3 pi g times rho, but rho is nu divided by A cubed. Remember nu? Nu was the mass per unit cell size. Nu over A cubed, that's rho. And there's g, or g is there, plus C over A squared. This is the new thing. C over A squared is the new thing that was not here in our initial study of this equation. What does it do? All right, so let's look at it first. This is the real Friedman equation with this other term on the right-hand side. And it was derived from general relativity, not from special relativity. Sorry, not from Newton. But nevertheless, we just derived it from Newton. Good. Okay, so here we are. Let's see what these things mean. Let's assume for the moment that the universe continues to grow. if C is positive, and everything else on the right-hand side is positive, 8, pi, g, nu, a cubed, they're all positive, then the right-hand side is strictly positive, and a dot over a is positive. In other words, the universe continues to grow. If a dot is positive, and a is positive, if a dot, the time derivative of a is positive, the universe continues to grow forever. It may slow down, but it will continue to grow, or at least it won't contract, and it will continue to grow. So if C is positive, the universe will continue to expand. It will eventually get arbitrarily big. By arbitrarily big, I mean that A will eventually exceed any bound and become very large. So let's look at it in the limit that A becomes much larger, very, very large.
Excuse me, why does a dot over a have to be positive? I mean, the square of it obviously has to be positive.
Right. The square of it is that's right. Good. The square of it has to be positive. So let's assume that initially it is positive, that the universe starts out expanding. Okay? Then the only way it can ever get to be negative is if it goes through 0. And it can't go through 0 if the right-hand side is positive. Good. So that's a good point. The right-hand side being permanently positive disallows this from being 0, and therefore it can only continue to grow. Can't jump from positive to negative without going through 0, and this is never 0. Okay, now which term here is bigger? 1 over a squared or 1 over a cubed? Well, that depends on whether a is big or small. All right, but in particular, let's go and think about very large a. Let's start with small a first. For a being small, which is bigger, 1 over a cubed or 1 over a squared? 1 over a cubed. If you take a to be small enough, this will always beat this. And so for a sufficiently small a, this is negligible compared to this. We've already studied the case without this, and we know the answer. We know the answer as long as a is small, in other words, in the very early phases of the expansion, when a is just starting out growing, is just beginning to grow, this term is not important. And what do we find? We found out when the term was absent that a expands like t to the 2/3. But now let's go to the other limit. This is a standard way of thinking about all kinds of things. Go to limits. Often an equation, this equation is solvable incidentally, but it's nasty. We don't have to solve it. We just have to know what it's doing at the two ends. The two ends mean when a is very small and when a is very big. Okay, so what about when a is very big? Which term is big? This term is the biggest term when a is big. 1 over a squared is much, much bigger than 1 over a cubed. You may have to wait a while, and how long you have to wait may depend on this constant here, but eventually this term will become much larger. So let's study that equation. Let's study the equation a dot over a squared is equal to some constant, any constant, over a squared. Okay. We first take the square root of it. And what's the square root of a constant? Another constant. So I won't change its name, but it's really, this new c here is the square root of the old c. And of course, the reason I'm allowed to do that is because it doesn't matter what the constant is here. We'll get an answer which is qualitatively the same for every c. All right, a dot over a is c over a. Now let's multiply by a. A dot is a constant. A dot is a constant. A dot is the velocity of the galaxy at x equals 1. In other words, in the situation where the energy is positive, when the galaxy gets far enough away, the effect of gravity becomes negligible and it just moves off with uniform velocity. That's what this is saying. A dot is just constant, And that tells us that A is just proportional to time. The constant c times time. The galaxy just moves off with uniform velocity. And so that tells us this is for positive c, for positive constant. C is not the speed of light here, incidentally, although it happens to be a velocity. All right. So it tells us that at late time, this just moves as a straight line with constant slope. A dot is just the slope, moves with constant slope, and the universe just expands with linear, unaccelerated, non-accelerated motion. Nothing as deep is going on here. Why am I using nuts when I should be using apples? All this is saying is if you throw this up hard enough so that it escapes from gravity with a good margin, then it will just move off uniformly with constant velocity. So in fact, we find that. We find exactly that. What happens in between? Where's the crossover point? Well, I'll leave that to you. You can figure out approximately where the crossover point is. It goes as t to the 2/3, and then makes a transition to just t and sort of fuzzy in between. That's the matter-dominated universe. Why is it called the matter-dominated universe? Because the right-hand side of this equation contains a term which is just the density of ordinary matter. Ordinary non-relativistic, slowly moving matter. That's it. Okay, so well, let's go to the other case. What happens if C is negative? That's the case of negative energy. Now you should be able to guess. A particle, or the apple moving away from the Earth with less than escape velocity, has negative energy, and it just falls back down. Huh? So that's actually not hard to work out. I'm just going to tell you what happens. What happens, first of all, what happens, then you have a negative sign here. You have a negative sign here, and now the right-hand side can become 0. Initially, this is the biggest term. At a late time, this is the biggest term, but they have opposite sign. That means somewhere in between, this became 0. That is nothing but the point where the upgoing apple simply is momentarily at rest, when A dot over A is 0. Good one.
There goes the laws of physics. There goes the laws of physics.
Okay. So with C negative, there's a crossover, and instead of moving off linearly like this, bang, crash. Everything falls together. That's the matter-dominated universe, and it was the classic cosmology until other things were discovered. Okay. Any questions? It must be that, my assumption when I get no questions is either I was perfectly clear or perfectly, yeah.
Well, I'm trying to understand this. So at some point, those two terms will cancel each other. You get 8 prime over A squared equals 0. But that other side always has to be non-negative. So
Which does?
the right-hand side always has to be non-negative.
No, this can become negative.
How can it be negative? 8 prime over A squared has to equal that thing.
Say it again?
Your left-hand side is always got to be non-negative. Hence, your right-hand side always has to be non-negative.
Oh, you have to take a square root.
Pardon?
You have to take a square root. Square root can have a,
Well, you take
right.
square root, just that equation there says that right-hand side, since the left-hand side is always non-negative, then the right-hand side is always non-negative.
Yeah.
So
But that's
I'm
because-
just wondering what happens if when it becomes 0, then it must become positive again or stay 0 or something.
No, I made an assumption that the universe was expanding, and that breaks down at the point where it comes to rest. The mathematics is entirely identical to this here. What would you write? You would write 1/2 mv squared is equal to g m over the distance. Am I missing anything? Times the mass of the Earth. No, minus this is equal to the energy. If the energy is negative, let's call it minus here, then this is plus gmm over r, basically, or over distance. It's the same equation. How does it happen if E is negative? If E is negative, then there can be a crossover point. It's the same, exactly the same thing, exactly the same thing. And you know what happens. You know that the apple just falls back down to Earth. It's just a question of taking the root. There's a plus root and a minus root of a square root. Yeah.
But I think what he's saying is 8/35 e whatever over a cubed has to be greater than equal to c over a squared. Otherwise, something squared goes negative, which is mathematically impossible.
You say this has to be bigger than this?
Or equal than that, yeah. I think that's what he means.
The point is, A can never get big enough to turn the sign of this. A can never get big enough. Let's see. If A is big, then this term is bigger, and it will go negative. But it never does get negative. No, okay, good. The right-hand side never gets negative. You're right. The right-hand side can never get negative. All that tells you is there's an upper bound on how big A gets. Right. A gets so big and then stops getting bigger and comes back down. A is always in a region where this is positive, but it goes through zero. And going through zero is just coming to rest and falling back down. Right. And on the way back down, you have to take the negative root. A dot over A is negative square root. Good. All right. Yes. Okay, so that is the matter-dominated universe. 3 possibilities: positive energy, negative energy, or zero energy, and 3 different behaviors. Who decides whether the energy is positive or negative? Who knows? But we're going to find out that the connection of that positiveness or negativeness is connected with the geometry of the universe. Not tonight. Next time we'll talk about the connection with this constant c with the spatial geometry of the universe. That's the main thing at this stage that general relativity brought to bear on this. The equations are exactly the same, but the significance of this constant c takes on a new dimension and has to do with geometry, but not tonight. One more thing we're going to do tonight. We're going to take up the question of what happens if, instead of being made out of material points, slowly moving, what happens if the universe is made out of photons, made out of radiation? All right, to understand that, of course, we really do have to think about relativity. But really, there's only one important idea, and it's just E equals mc squared. If we were to have done Einstein's equations, the right-hand side of Einstein's equations here, the right-hand side, the left, basically, all right, I'll tell you what the connection with Einstein's equations is. On the left, we have A dot over A squared, and then I'm going to add plus C over A squared, transpose it to the left, and on the right-hand side, good old 8 pi over 3G Rho. Nu over A cubed, or just Rho. Now, this is mass density here, but Einstein's equations are of the form that something on the left having to do with geometry is equal on the right side to things that have to do with the density of energy and momentum. Energy momentum tensor on the right-hand side, geometry on the left. This clearly has to do with geometry, the rate at which the universe is expanding. I'm going to tell you next time that C over here has to do with the curvature of space. So this side here is Einstein's geometric side. The right-hand side is the source, namely the energy, momentum, whatever it is in the universe. What is the energy on the right-hand side of this equation? It's just the mass points and E equals mc squared. So, oh my goodness, I'm calling this C, but please don't get the idea that it's the speed of light. It's sometimes called kappa, minus kappa. It's sometimes actually written minus kappa. Unfortunately, kappa is positive when the energy is negative, and kappa is negative when the energy is positive. But it's often called kappa. Okay. That's the basic connection with the general theory of relativity. But the only thing that we really need to do to this equation is to remember that when you go from Newton to relativity, what was mass density becomes energy density. All forms of energy density are what go on the right-hand side here. Well, it's energy density times the speed of light squared. Is that right? M is E over C squared. So it's energy density divided by C squared, which goes on here. We'll just set C equal to 1. We're not going to worry about the speed of light. Speed of light, C, is equal to 1. With that idea in mind, the right-hand side, instead of being the mass density, becomes the energy density, total energy density, some of which is just the E equals mc squared energy of the particles at rest, and some of it might be kinetic energy of particles, which we haven't really included at this point, the kinetic energy of a relative fast motion of them. But if the universe is filled with photons, then it's radiation energy. All right, so let's talk about radiation energy and how it's different from the E equals mc squared energy. All we have to do is think about a box. A box now, the box just corresponds to a unit cube in the grid here. Take 1 unit cube of the grid. It has a volume of A cubed. Let's suppose it has a certain number of photons in it. Now, photons have a wavelength. So here's our box. It's delta x equals 1 on each side. Its volume is A cubed. The ordinary particles, which are just sitting in that box and not moving, they have an energy which is just their mass. It doesn't change. Right? Their energy doesn't change those particles. They're just their mass and nothing else. But a photon behaves differently. So I'll tell you how a photon behaves. The first thing to know about a photon, or electromagnetic radiation, first thing to know about a photon is that its energy is related to its wavelength. It's related to its wavelength through Planck's constant, h. What else? Lambda, the wavelength. And the speed of light, which I'll set equal to 1. Important thing is that it's 1 over the wavelength. Now, something which I am not going to prove, but I'm going to tell you, is that if you take a box with a photon in it of a given wavelength, let's say you have a photon of a given wavelength, and you expand the box. You expand the box slowly, for example. Then the universe is expanding pretty slowly. It takes 10 billion years for it to double in size. It's pretty slow. You take a box and you expand the box slowly, then what happens to the photons inside it? What happens is the photons inside is their wavelength just stretches in proportion with the box. Now, this phenomenon, anybody who plays a guitar knows the phenomena very well. The box is replaced. Here's the string of the guitar. It's pinned down at one end, at the bridge over there. At the other end, it's pinned down by your finger at the fret. And you pluck it. It starts to vibrate. And then if you slide your finger, what happens is you slide your finger, you're effectively changing the size of the box. This is changing the size of the box. You change the size of the box, the wavelength just changes, and the tone, the note changes in correspondence with a change in the size of the box. The same thing happens to radiation in a box. Radiation in a box, the wavelengths just stretch in proportion to the size of the box. Because the wavelengths change for the photons, that means the energy of each photon changes as you change the size of the box. The world is filled up with photons. You can pretend that the number of photons in each box stays fixed. That's a true statement. Number of photons stays fixed, but their energy changes as you change the size of the box. In particular, the energy of each photon will be proportional to 1 divided by the size of the box. So we take one box, change the scale factor, then the energy of each photon decreases. Same phenomena as the frequency going down or up as you change the length, the effective length of the guitar string. So what does that mean? Yeah.
That makes sense if the box is conducting and the electric field has to go to 0 degrees, then that makes sense, but you don't have conducting boxes in space.
Don't you get the same thing if just you have free space expanding? You get the same result.
I mean, one way I've thought about it is, like if you had mirrors, this box is made out of mirrors, the mirror's moving away and you get a Doppler shift when the photon goes back.
That's one way to think about it. It's one way to think about it.
Last week you said that the expanding universe is sort of a mathematical artifact, and that you can just think of particles.
I never used the word artifact. You did.
But you agree with me.
It depends on what your conclusion is.
Okay, well, that's what I'm trying to understand is that clearly there's something more going on where the wavelength wouldn't change.
Yeah, that's right. Yeah. We'd have to do a little more quantum mechanics or a little more classical electromagnetism in the presence of an expanding universe to justify what I said. Okay. Let's take it for the moment as a given, and we can come back to it. The answer, it is a correct statement that and let me see if I can think of an example. Offhand, I can't think of a good practical example where something similar happens, but nevertheless, it is true that the radiation in the box, the wavelengths of the photons readjust themselves to the sizes of the box. In other words, the photons stretch along with the universe. If you like, you can just think of the space stretching, and with it, the photon wavelength stretches. Let's leave it at that for tonight. For tonight, let's leave it at that. Let's just examine the consequences of it. Let's examine the consequences of it. The consequences of it is that the energy per photon decreases like 1 over A, in contrast to the case with ordinary particles where their mass stays the same and doesn't vary. So by contrast with the particle case, ordinary particle case, the energy in the box, the mass in the box, effective energy or mass, does not stay constant, but it decreases. Total energy in the box decreases like 1 over the scale factor. Every photon, its energy decreases when it gets stretched, so every single one of them. And so compared with the previous case, there's one more factor of A in the denominator. The energy in the box goes like 1 over A, and the energy density goes like 1 over A to the 4th instead of 1 over A cubed. Remember previously, the density here we said was some constant nu divided by A cubed. Now we get one more factor of A in the denominator, and it's just the fact that every particle, its energy decreases by 1 extra power of A. That means, relative to the previous case, there's an extra A in the denominator. Nu could be taken now to be the number of photons per unit in a box, and the energy would be 1 over A to the 4th. That's the only new thing that happens. This is matter dominated, and this is radiation. A dot over A squared, again, 8 pi over 3, G, some constant nu, and then A to the 4th downstairs. We can also put in this term here, minus C over A squared, but let's study the case when the case that corresponded to 0 energy, just to see the difference. To see the difference. Let's see what different behavior we get with this formula. This formula says, oh, again, by appropriate choice of the size of the grid, you can make all the constants here, if you like, be 1. By appropriate choice of the size of the grid, you can rearrange it so that it's just A dot over A squared is 1 divided by A to the 4th. What was it before? Do you remember? 1 over A cubed. Okay. So let's see if we can figure out what happens. Again, we're going to solve the equation now. We're going to go through the steps of solving the equation. First, take the square root. A dot over A equals 1 over A squared. That means that A dot is just 1 over A, right? Did I do that right? That's the A dt. All right, we'll do the same trick as before, turn it upside down. dt by dA is equal to A. So now, if we think of A as the independent variable, we're looking for a function whose derivative is just A. What function has its derivative A? A squared, right? Yeah, A squared. 1/2 A squared to be exact. So that says that t is like A squared. Maybe there's a 1/2 here, but that's not important. The thing is that t varies like A squared, or that the scale factor varies like t to the 1/2 square root of A. Well, I'm not much of an artist, and I can't really draw the difference between t to the 2/3 and t to the 1/2. There's t to the 2/3. T to the 1/2 is a little bit smaller, huh? Doesn't grow as fast. So t to, but it looks pretty similar. And does pretty much the same thing. You'd have to be an astronomer who are really interested in this to care about the difference between t to the 1/2. By that I mean, they're sufficiently similar, qualitatively similar. But if you really want to know what's going on in the universe, the difference between t to the 1/2 and t to the 2/3 can be very important. Okay, so that's the radiation-dominated universe. The radiation-dominated universe expands like the square root of t, not t to the 3/2, t to the 2/3, t to the 2/3, t to the 2/3 and t to the 1/2. What about the mixed case? Supposing a universe has both ordinary particles and radiation, like the real universe really does. Let's worry about that. Let's come to that. The mixed case, neither pure radiation nor pure non-relativistic particles. In that case, the energy density is two components, one for radiation, that goes like 1/8⁴, and one for ordinary matter that goes like 1/8³. So the kind of equation that we're going to have, I'm not going to write the details, I'm going to write down the general form of it, will be a dot over a squared. And that's going to have two terms now, one of which, call it constant number 1 divided by a³. That's ordinary particles. The constant C1 is just some measure of the number in each box. And then another term, and they're both positive. The energy of particles and the energy of photons is positive. And the other is some other constant over a⁴. That's the equation of motion for a universe which contains, like our real universe does, ordinary non-relativistic matter plus radiation. Which one is more important, 1/8³ or 1/8⁴? Depends on A, right. When A is big, which one is more important? This one. Excuse me. My mother always told me not to take such big bites from the apple. For small a, this is the more important. And the smaller the a is, the more important it is. When a is big, this is the more important, and again, swamps the other term when a is really big. So what that tells us, without too much work, is that when a is small, in the beginning of the expansion, the only thing that's important is the radiation. This one. The radiation term is dominant compared to the material protons, neutrons, galaxies. There were no galaxies at the beginning, but and the radiation was the most important thing. And so the universe started expanding like t to the 1/2. But then, eventually, this term took over, became the more important term, and it made a switch. Let me get another color. It made a switch. And started to grow like t to the 2/3.
You're assuming that the proportions of radiation and matter remain constant.
Yes. Yes, that's correct. That's correct. And you might say, well, how do you know that energy of matter doesn't get converted to energy of radiation? That's something we're going to have to discuss. The answer is when things get cold enough, when the universe expands enough, things cool down, and there's not much exchange between radiation and ordinary matter. And they are pretty well conserved, each one separately. They don't talk to each other too much. In fact, once things cool down to a certain temperature, it's a rather high temperature, 1,000 degrees, or more than 1,000 degrees, 10,000 degrees. But once things cool down to a certain temperature, pretty much the photons are just free streaming and don't care much about the particles. And the photons are too long wavelength to even scatter the particles very much. So that's right. That's exactly right. That we've assumed that the two constants here are pretty much time independent. All right, that's the nature of a universe built of two components. Now, that's only two components. That's only two components, and there is a third component. There is a third component. It's the discovered dark energy. That's what we're going to talk about next time. We have ordinary matter. We have radiation. Those are commonplace things. Dark matter belongs to the matter category. It's simply a part of the ordinary particle matter that's invisible simply because it doesn't have any charge, doesn't radiate much, so we don't see it optically. That's part of C1. This should be C2 here. I meant to write C2. Or maybe we should call it Cm for matter and C radiation for radiation. There's more than one component to the radiation. There's photons. There's presumably gravitons. And there are neutrinos. Now, neutrinos have mass. Okay? But the mass is so tiny that even today, the neutrinos are moving with very close to the speed of light and simply mimic the same behavior as the photons. So there's a radiation component. The radiation component consists of all particles which are so light that they're moving with close to the speed of light. The C1, or the C mass here, consists of all particles which are heavy enough that they're basically at rest relative to us nearby. And that's cosmology, sort of as it was known 30 years ago. This is the cosmology of 30 years ago. Yeah, Art.
So in that box that's expanding and the wavelength of the wave is stretching out, the total energy inside the box is decreasing. Where is that energy
The
going?
energy is doing what?
Decreasing.
Decreasing, yeah.
Where's it going?
Doing work on the walls to expand it. Well, another way to say it is it's going into the kinetic energy of expansion. This equation is, remember what it was? It was the equation of conservation of energy. That's where it came from. So if you think about it that way, then start tracing. If this part of the energy decreases, then, or let's put it this way. Let's write the equation in a different form. Let's put a minus sign over here. Well, no, let's first, one step at a time. Put minus, and make it equal to 0. I haven't changed anything. Now change the sign of the whole thing. Minus, plus, plus. This equation reads the following way, that there's a certain amount of energy and mass in radiation. If it changes with time, that energy gets transferred to a negative term. What's a little bit bizarre is that the energy associated with the kinetic energy of expansion, this term here is negative. This can be read as a conservation of energy. It can be read, energy never changes because it's always 0. Contains 3 terms, matter, radiation, and a term that has to do with the rate of change of expansion. Normally in the ordinary world, when the rate of expansion is very, very small. It's a tiny, tiny number. This here is a tiny, tiny number in our world at the present time, a tiny number. This never changes very much. And so it's not 0. I take it back. This is not a tiny number. It's a number, but it doesn't change much over a course of time. The sum of these two is 0, and it stays 0. That's the conservation of energy. Am I saying that right? I'm not saying it right. Yeah.
Conservation of energy is a symmetry with time when you think about it in terms of the Noether charge. Would the fact that A is time dependent sort of excuse you from conservation of energy?
Mm-hmm. There's 2 ways to think about it. you could say the universe is a time-dependent background that everything moves in. And because the universe is time-dependent, that means all of your equations have a time dependence. There is no longer a time translation symmetry, and energy doesn't have to be conserved. The other way to say it is that there's a time translation symmetry. If you start the universe at this time, or that time, or that time, or that time, you get exactly the same response. If you started the universe at t equals -7, it would be exactly the same as starting the universe at t equals +4. And thinking about it that way, you'll discover there's another term in the energy associated with the expansion rate. Let's not go into it now. This is very, very subtle, and I want to spend at least 15 minutes on it later. Energy conservation. But just do keep in mind that these equations, their origin was energy conservation. So there's no way that we can be violating energy conservation. Yeah.
Yeah, you said that Friedman equations are interesting because you can derive them through Newtonian mechanics or general relativity. Newtonian mechanics presupposes a flat geometry, and relativity assumes a curved geometry.
A geometry of space. Forget space-time for a minute.
Okay.
Right. Let's go about geometry of space. Einstein's equations permit flat space. These are, okay.
Would that mean that space is flat because you can derive it from either, not space-time, but just space? Would that be a conclusion?
There's our equation.
I think you erased it.
Yeah. Okay. Minus some kappa over a squared, okay? This had to do with the total energy, the fixed total energy. If kappa is positive in this equation, the energy is negative. If the kappa is negative, the energy is positive. Sorry, it goes this way. Kappa is minus the energy, essentially. Do I have it right? No, I have it wrong. I have it wrong. Okay, doesn't matter, one way or the other. This term over here has to do with the curvature of space. So we're going to study three cases. There are three interesting geometries that we'll be interested in. There's a flat geometry, where space itself is flat. This goes on and on endlessly, homogeneously, and triangles have the usual properties. That's the case k equals 0. There's the case where the universe is curved like a sphere. So if you go around it, you come out the other side, you go around it. Finite and compact, we say. That's the case k equals positive. Any positive number here corresponds to a radius of curvature of the expanding universe. Expands like a balloon, you know, the classic picture of the expanding balloon. That's k equals positive. K equals negative is a negatively curved space, and we're going to have to talk about what a negatively curved space is like. Less easy to visualize than the sphere. So the next time, it's exactly what we're going to do. We're going to talk about the geometry of space and the three cases: flat, positively curved, and negatively curved. They correspond to k being 0, positive, or negative.
So would that mean then that in the Newtonian case, k has to be 0?
Well, except that you can sort of mimic up the case with k not being equal to 0 if you want, but it's a little bit of a fake.
Okay,
Yeah.
it's a little bit, yeah, okay.
Right.
Question, a box full of photons where the box is expanding and the number of photons stays the same, the energy
Yeah.
would be going down to that box. What happens, where does that energy go? You may answer that question, but I don't understand. Where does that energy go?
It does work on the box. If you take a literal box with reflecting walls. Take a box with reflecting walls. and ask what happens to the energy in the box when you expand the walls. Okay? Well, what does happen? There's pressure in the box. There's pressure exerted by the photons bouncing off the box. The pressure, when you expand the box, does work on the walls of the box. For a real box, the energy could go to a number of places. They could go to stretching the distance between the molecules in the box. It could go into making kinetic energy of the walls of the box. But one way or another, it does work on the box and increases the energy of the box itself, either by stretching the little Hooke's law springs that are inside the box that hold the molecules together, or causing the box to have a kinetic energy, in other words, a kinetic energy of expansion, or whatever else, just heating the box.
So that energy has to be going into space, into the grid, right? But you said the grid is actually absorbing energy, is that correct?
Yeah, in a sense, that's right. Yeah. Right, we'll talk about that. We'll talk about energy conservation more clearly. Right, but it's a correct thing to analyze it. This is not obvious, but it's correct. It's correct to analyze it as if it were stuff in a box. And the stuff that gets reflected off here from a real box with reflecting walls is compensated for in the fake box case by every particle which goes across here is approximately compensated for by a particle which comes in the other side. So on the average, the expanding space behaves like an expanding box. Particles, instead of reflecting, go from one box to the other, but on the average, as many particles go from this box to this box as from that box to this box. And so in a sense, it can be mocked up by saying that the particles reflect off the box. Increasing the size of the box means that work is done against the walls, and we'll have to talk about what that means in general relativity when we come to it. Yeah?
Couple of questions. One, how soon after the Big Bang did the universe cool down to where the matter and radiation components were not really interacting or even changing?
About 100,000 years.
And then second one was, what astronomical evidence do we have to see the θ 1/2 behavior? Is that in the
What do we have to say it again?
What evidence do we have to observe the θ 1/2 expansion behavior? Is that in the cosmic microwave background?
That's the expansion history of the universe. And remember that looking out at the universe, you effectively see a history. Looking to different distances, you're seeing the universe at different times. So by looking at the universe at different times, assuming that it's homogeneous, you can reconstruct the history of expansion. We'll talk about that. That's something that we can do. Basically, by looking at the combination of density of galaxies on the sky, distance of galaxies, and we'll spend a little bit of time going through that, the combination of careful measurements of distance, density, and so forth allows us to reconstruct the history. And we can reconstruct the history because we're seeing it at different times.
It seems like the θ 1/2 behavior would be before galaxies formed.
Indeed.
But we can still infer.
Yeah. Yeah.
Wouldn't that be
Yeah.
sensitive to the Big Bang nucleosynthesis? I mean, wouldn't we be off on those calculations if it didn't do
You
T
bet.
1/2?
Yeah, yeah. And combining it with CMB and all of those things, yeah. Yeah, it was before galaxies formed, but in the temperature history of the universe, there's plenty of evidence that this picture is right. No, you're right. The t to the 2/3 is easy to see. The t to the 1/2 is largely has to do with microwave background and things like that. So, but get the equations down, and then we'll go and talk about how we know how much of this picture is right. And the answer is we know it's wrong. Yeah. Okay. Yeah.
So I think that this isn't a problem, but I don't understand why.
I can't hear you.
I said I think that this is not a problem, but I don't understand why.
Okay.
The apparent speed of an object relative to any observer is a function of how far away it is in expanding.
Yeah.
So conceptually, it seems like an object far enough away could appear to be exceeding the speed of light. But I don't think, that doesn't violate this idea of nothing can exceed the speed of light, but I don't understand why.
Well, you have to ask what it really says, what the principle that things can or can't exceed the speed of light. What it literally says is you can't see anything going past you at faster than the speed of light. It doesn't say that two objects in an expanding universe can't be receding from each other at faster than the speed of light. That is quite allowed. And as you point out, that if you have a formula which says velocity is equal to distance times the Hubble constant, and you make the distance big enough, the velocity will, sure enough, exceed the speed of light. It's connected with the idea of a horizon. But you're right. These equations say that things can move, recede from each other at faster than the speed of light. And, but for sure, they don't allow you to send signals in time faster than the speed of light could get from one place to another. And they don't allow you to witness something moving past you faster than the speed of light. So it's right.
Does this mean that objects sort of at the limit, right before where the expansion rate exceeds the speed of light, eventually disappear? In a sense, if you know what I mean.
Yes, they'll pass through the horizon and we won't see them. Right. But that has to do with dark energy. Oh, that has to do with dark energy. Without dark energy, nothing would really move out of our ability to see. Right. And I will show you how the geometry works, and I will show you how all these things can be understood. But little steps. Good. Okay.
Professor?
Yes.
Is the beginning of the saying that we'll never see more of the universe, no matter how long we wait than we do today, is that related to the fact that objects far enough away are receding at a speed faster than, would appear to be traveling faster than the speed of light?
It's more than that. It's the accelerated expansion of the universe. That is true. That is true, but the universe will slow down. No, sorry, excuse me. If this picture were right, and the universe were to slow down, then things which are currently moving away from us faster than the speed of light would in the future be moving away from us with less than the speed of light. And at that point, they would become visible. So if this were the pattern, eventually we could see everything no matter how far away. Okay? This is not the pattern. The pattern is that. And if this pattern is correct, then there is an ultimate limitation that you cannot see past a certain point. But let's hold back on that. We're going to spend a lot of time on those particular things. Those are the really interesting things, and we'll explore them.
The way I've always thought about the question of why when the box expands, the radiation, the photons lose energy, is that there's a wave phenomenon going on, the wavelength's increasing.
Yeah.
Is that a reasonable way to think about it?
That the wavelength increases.
Yeah. 'Cause
Yes.
space is expanding.
Yes.
So the energy the photons go is decreasing because their wavelength.
That is correct, The question is, why do you have to suppose that as the universe expands, that the wavelength of a photon will match it? Why is the wavelength of the photon sort of rigidly attached to the grid, if you like? That's the question. Why is the wavelength of the photon somehow rigidly attached to the grid? Now, anybody who knows a little bit about waves and wave propagation knows that there's what's called an adiabatic invariant. The adiabatic invariant is the number of nodes, the number of times the wave passes through zero. And as long as you change things slowly, the number of nodes stays fixed. This is called an adiabatic invariant. And if we had some sort of closed circle that waves could propagate on, this is something in principle we could build. And we have waves propagating on it. And somehow well, I was trying to think of an example. I couldn't think of one. I still can't think of one. But imagine we have a dial that allows us to change the radius of this ring here that things are propagating on. In other words, change the circumference of it. Changing the circumference of it will not change the number of nodes. You might ask yourself, how could it change the number of nodes? Suddenly? I mean, we're going to change the radius gradually or continuously. At what point would you expect here? How many nodes were here? About 10 or something like that. You know, everybody know what a node means? Number of times that the wave goes to zero. Right? It has to be integer. For one thing, it has to be integer. The wave, in going around, a standing wave. Let's take a standing wave for simplicity. A standing wave on here has to go around and be periodic. So the number of nodes has to be an integer. Okay? Now you start stretching the space that it's propagating on. It can't suddenly jump. At what point is it going to jump from 7 nodes to 8 nodes? It doesn't jump. What it does is the waves just get longer wavelength and shorter wavelength to match the thing that it's on. It's the same phenomenon, except replace this ring by the universe itself. Number of nodes, number of zeros is invariant, never changes, and the only way that can be accommodated is if the wavelength of the photon increases, wavelength of the wave increases. Now, any wave, even if it's not a nice thing like this, let's suppose it's just a lump over here and then nothing, and nothing over here. By Fourier analysis, it can still be expanded in waves that have this nice periodic smooth structure. Each one of them has a number of nodes which is fixed, and so that's good enough for us. The individual waves of definite wavelength can't jump the number of nodes, and so instead the wavelength has to accommodate the size of the thing that it's propagating on. Yeah?
As you look out in the universe and galaxies move faster and faster, relativity says the mass of them relative to us would grow as things move faster and faster, correct?
The energy.
The energy, yeah. Okay.
The kinetic energy.
Okay. If we were to weigh it, it would weigh more.
Well, you can't weigh something that's far enough far away. No, it's important. It's important. But go ahead.
Yeah, I think you may have answered my question, but assuming it grows continuously, at some point it goes exactly at the speed of light, which means the mass must be zero?
Infinite. Mass. No, oh, sorry.
Yeah,
Sorry.
the momentum.
Mass is a thing that never changes.
Yeah,
Mass never changes.
Yeah.
Mass of the electron is always whatever it is.
Yeah, I think what it means is the question itself is silly, because you can't talk about the mass, you got to talk about the energy and the momentum.
You have to talk about the energy.
Okay. So from a naive perspective, mass goes from really, really a lot to zero, since things with mass can't go at the speed of light. But as you just said, that is not the way of thinking about it.
No, that's not
Yeah,
the way of
I understand.
Right. Well, look, to do, yeah, okay.
Things move faster than light. Wouldn't the time and space,
What's that?
time and space axis gets interchanged, right? I mean, how does that thing work out?
How does which thing work out?
I mean, if you just said if things which are far away start moving faster than the light, then at that place, what we see as what we refer to as a space, swapped with what time axis at the place is. So,
Why don't we wait? Why don't we wait? We're going to talk a great deal about horizons and the geometry. We cannot. The point is, we cannot analyze those kinds of questions by just thinking in terms of Newtonian or even special relativistic geometry. We have to analyze them by saying there's a metric, that there's a geometry, and we have to analyze that geometry. And we will do that. We will do that. We can go only so far without introducing real relativity. So far, we've been okay. We didn't have to introduce relativity. And the reason why is because we stuck to a small enough region. All these equations were derived by looking at galaxies which did not have to be very far away. All right, we follow some galaxies which are reasonably close, and we follow them. If they're close enough, they'll be moving with a very tiny fraction of the speed of light. So that's what we did. We followed things which were close enough that they never got anywhere near the speed of light. If we want to study the whole universe and out to distances where the Hubble constant times the distance is comparable to the speed of light. If we want to study the universe on that scale, then we can't do it without relativity, and we really can't do it without general relativity. All right, so you're jumping ahead of the game and trying to get there thinking only about Newton and special relativity.
Coming back to the energy of the photon, just by stretching the wavelength, how does it decrease the energy of a single photon? It's more the density that is decreased, right?
What's that? Say it again.
If you stretch the wavelength, you said that the energy of an individual photon decreased. All that happened was that the energy is spread over a longer wavelength.
No. The energy itself decreases. And the easiest example is to think about the photon in the box or the violin string. The photon in the box exerts pressure on the walls of the box. Because it exerts pressure on the walls of the box, it does work on the box as it expands. The work is the pressure times the change in volume, and that's equal to the change in energy of the photon. So the photon is doing work on the box, and in doing work on the box, its own energy is decreasing. Look, this is also true, incidentally. Forget photons. Just take ordinary particles, a gas in a box. What happens to the temperature in this box if you increase the volume? Down. What does that mean about the kinetic energy of each particle? It goes down.
If you do it adiabatically, or if you do it
Adiabatically.
infinitesimally slow, if you do it infinitesimally slow, it doesn't go down, does it?
If you do it infinitesimally slow, it does or does not?
Does not.
It does. Yeah. If you do it very, very suddenly, what will happen? If you do it suddenly, here's the molecules, okay? And you absolutely, instantaneously, suddenly increase the volume of the box. What you find is a big empty space. The molecules are still in the original volume here, and nothing has changed, their energy, their momentum, or nothing else. That's the non-adiabatic case. The adiabatic case means you increase it slowly, and slowly means there's plenty of time for molecules to bounce off the walls many times. Then it will cool. If you do things suddenly, it's likely to heat, even if you expand or contract. If you do things really suddenly, it's likely to heat, or at least not cool. But if you increase the volume of the box slowly, then it will cool.
Isn't the whole redshift the same as this wavelength increasing, the scale?
It's connected, yeah. It is connected. Yeah. But it's a phenomenon that doesn't particularly have to do with photons. It simply has to do with pressure against the wall, and increasing the box means that work is done by the pressure on the walls of the box, and to conserve energy, it has to cool. So this is the phenomenon of the photons cooling. Okay. Good.
For more, please visit us at stanford.edu.